And we're gonna start this page is page 10. I'm gonna go through this example problem that will clarify almost everything. That's what I feel. So this is a 2 degrees of freedom system. I'm pretty sure I cover all this. But I want you to carefully read, so at least a few hours I want you to spend the rest of the chapters, things like that. Of course, I'll give you a full lecture, and you should have a full understanding what's going on here. So this particular problem, as I said, a 2 degree of freedom system problem. How can you tell that? By looking at that, what determines the degrees of freedom system? Hey, look at me. This is late. It's 6 o'clock, but by looking at this, can you tell this is a 2 degrees of freedom system? Everybody agree? You know? 2 degrees? Not sure? Chongwan? It's yes, you said. How can you say, what tells you this is a 2 degrees of freedom system? 2 coordinates to define the motion of the system. So this system contains the 2 degree of freedoms. What does it mean, degree of freedom? Anybody can comment on it? Degree of freedom. Hassan.
Move in 2 coordinates.
Yeah, it's a degree of freedom. It's like the coordinate freely to define the motion. So to define the motion completely for this particular system, you need 2 coordinates, independent coordinate, which is x1 and x2. So this is a planar system. It doesn't move out of plane directions, just in plane direction, one direction. It doesn't move up. We have a constraint on that. It's moving horizontally. Always such a lumped mass system, coordinate is drawn at the mass. Okay? For the plate, that's a continuum system. Then you break it down into pieces. Then you can determine the degrees of freedom at every node. So any node in space, you can define the motion of that node using how many coordinates? How many? 6 coordinates, right? 3 translation and 3 rotations, right? Any point can move in x, y, z direction, and also rotation about the x, y, z direction. So to define the motion of any node, any point, or any particle in the space, you need 6 degrees of freedom. But this particular planar, and also the motion is constrained in all other directions except the horizontal direction, so you need 2 coordinate, independent coordinate to define the motion, drawn at mass 1 and mass 2. Okay? And also, tonight is much more comfortable to me because I don't have to finish by 50 minutes, you know. So you have two mass systems there. So it has a roller, frictionless roller, and you have that, and you have that, then this. So this is mass m, right? This is mass m. This is mass 2m. And the spring is concerned, this is K and K. Then you said, okay, this is X1 and this is X2. To get the solution, to get the equation of motion, all you have to do, easiest, the simplest way is to draw the free body diagram around the mass m and around the mass 2m, then just apply the Newton's second law. But if I say that, okay, this is the system, but if I do this here, oh, this is that, we have more springs. We have more springs. We have springs here, right, and here. We have a connection. This is K, K. It doesn't matter how many springs you attach, that does not change the number of degree of freedom system. Doesn't change at all. But now, what I'm going to do is, I have a spring, I have a spring, I have a roller here, of course, roller here, of course. So I'm going to take this spring and take this, cut it, then put it out here. Then is this two system identical, or the two systems are different? Is identical or different? That's the question. By intuition is the best, right? As engineer, to have a good judgment. Not the math first, but physical meaning. Intuition is the first. In your intuition, these two systems, system 1, system 2, is this identical system or this is not? Well, democratic society, we have to take a vote. Identical, raise your, just to feel free. This has nothing to do with the grade. Forget about it. Identical, raise your hand. Okay, 1, 2, 3, 4. Don't look at other guys, what he's doing, whether he's raising his hand or not. Identical. 1, 2, 3, 4, 5, 6, 7. Okay. Identical. 7 guys. Not identical, raise your hand. 1, 2, 3. Okay. So 3. Well, you are buddy each other, so you have to support each other, so it's identical. Okay, Willis, why this is identical? What makes you feel identical?
Because the equations of motion and you roughly work it out, it's still the same.
How about Gusto? You said that this is not identical. You might have a feel. Just feel free to tell.
The first one is you pull it out, and the second one is you push it.
Okay. First, let me tell you the answer. This is identical system. because it's 7-3, so 7 is a winner. No, that's not the reason. But Gusto, he almost tell, but his answer is opposite. But let's look at this. So this is better. So Newton's second law is what I said you should. Let's look at the free body diagram around here, around M. So which means if you just press X1 in the positive direction, which is the direction to the right, okay? If you press it that direction, this is simply Kx1. If you cut the spring, you have to hold in that direction. So this is Kx1, okay? And now for the middle spring over here, so I'm going to apply X2 and X1. So you can do either way. I'm going to just pull it X2 to the right, X1 to the right, positive the X direction. Then let's assume X2 is the lengthwise is higher than the X1, let's say. Then what happens? If you cut the spring, middle spring, then what do you expect? The force apply what directions for this mass, M. So X2 the length is higher than X1. Then what happened? Then it moved to the right, isn't it? When you cut the spring at the middle, then you have to pull it, right? Because length, X2 minus X1, that's a positive. It's in tension. Makes sense? That makes sense, right? X2 is larger than X1, then spring gonna be stretch. So that's what this case is. Is in that direction. And also when you cut it, this is equal and opposite. Otherwise it will fly away. So it's gonna be equal and opposite. When you set up the free body diagram this way, you will never screw up. And you can think the other way. You can solve it yourself. X2 is smaller than X1. Then spring gonna be compressed. So that case is X1 minus X2. That's a positive number. Then direction of the force is opposite. This is in compression. Pressing. So you will end up having the exactly same result because of the sign as you're doing it. So now this is very clear. When you move X2 in that direction, then spring is in compression. So it's going to be pressing to the left. Simple way. So now that's a Kx2. When you have, I cut it, put this in here, so I just cut it, put it the other side because it's tied on that mass. Then what happens? If you press it, this spring gonna be in compression. So it's gonna compress that direction. So it's identical. There's no difference. That whether you put the spring in that direction or that direction, identical. Do you see that? You see that? So this is then around here, you can apply Newton's second law. M1 times X1 double dot. Inertial force is equal to summation of all the external forces. which means we've set that direction is a positive plus kx2 minus x1. This is a negative minus kx1 right here. For this one, m2 x2, m2 times x2 double dot is equal to, this is a minus, this is minus. So minus, minus. So then you can cast into matrix forms, right? Once you have that, then you can see m1, which is m x1 double dot. Then next you can put this guy back in to the left, that guy to the left, minus x1 times k, minus kx1 is twice. This is negative here. Then move to the left, you have a positive. First term at the middle is 2k, right? Because it's I'm sorry, you're talking k is a 2k because the spring is concerned. It's a k and k, 2k. And x2 is concerned, kx2, when you move this guy to the left, it's a minus kx2. It's going to be the negative, right? So that's the way you set it up very easily. So mass is m0 and 0 to m, if you just put it this guy. Then characteristic equations. So we got this in the previous page. And minus omega square, we know this, we know that. Then determinant of 2 by 2. So you can solve, then plug in m and k here. Then you multiply these two terms. Then minus of multiplication of the two terms. So this is omega square, omega square. So this is order of omega is the fourth power, right? So you have that equation. If you say omega square is lambda, okay, so then this is a quadratic equation with respect to the lambda, right? You see that. Because I set the omega square as a lambda because there's eigenvalue. We're nothing but solving eigenvalue to get the natural frequencies and mode shape, or eigenvalues and eigenvectors. We got that. So to simplify the equation, I reset capital omega square as a k over m, just to simplify. Then if you divide by everything by 2m square, so omega, just leave everything as is. So in this case, if you replace this guy with this notation, you have that. It's a fourth order of omega, but in fact, that's a second order quadratic equation with respect to the lambda, which is omega square. So it's two things you are really working on. So phi is eigen matrix. So to get this, you got, as we discussed in the morning, you have n different number of vector, which is eigenvector. So when you solve this equation, this is a quadratic equation. Don't look at it as a fourth order equation. Quadratic. If you replace omega square as a lambda, That's a quadratic equation of a lambda. So then you can determine the omega root, which is eigenvalue over natural frequency here. But if you have the quadratic equation, how many roots do you expect? 2 roots, quadratic. But this is a 4th order. Then how many equations do you anticipate? 4 roots. But negative doesn't mean anything to us. Negative natural frequency doesn't mean anything. You throw away. Keep the positive root, which is here is omega 1 and omega 2. I want you to, I just skipped a couple lines between, but you can very easily derive yourself, okay? Omega 1, 0.79 square root of k over m. This is about twice. You can tell roughly, this is about twice because mass is about double. So omega 1 and omega 2, step by step. It's easy. First step, set up the equations of motion. Then apply the characteristic equation to get the natural frequency. In this case is omega 1 and omega 2. Then next bring back this equation, characteristic equation back, which is this. Where did you get this? You got a couple page back here. Couple page back. This is the equation. This is the equation we have. That equation comes from this equation set. From here. So it's all spelled out there. You don't need any additional references. So you have that. Then just expand this guy out. This phi vector, you have entry phi 1 and phi 2. So you have a phi, you have 2 entry, you have a phi 1, you have a phi 2. Okay, so that's what that entry is. So just expanded the form here. We know M, we know K, we just put that in. And R is 1 and 2. What's R? The mode. First modal frequency, second modal frequency. We have 2 degrees of freedom system. So you have 2. R is equal to 1 and 2. Okay? Then phi R is, this is a transpose. You can spell out in a row for the vector. Then rewrite the above equation means this guy. To simplify it, divide by, K. Then you have that expressions right here. Then from here, you can substitute R is equal to 1 first for the first mode. Then you replace R equal to 2 to get the second mode. So it doesn't matter whether you use the first equation or second equation. It's identical because right hand side is equal to 0. As you see here. Okay? So here, if you do that, this is for the R is equal to 1 for the first mode. Phi 2, the first mode is equal to, by looking at this, is this. Then you can determine phi 2 is equal to 1.366 times phi 1. ratio is important. Over here, ratio is important for the mode. I told you even this morning, mode has nothing to do with actual displacement. So over here, the V2, first mode, is equal to 1.366 V1, which is R is equal to 1 situation, which is the first mode. Or, if I rewrite this, V2, V1 is equal to 1.366 over 1.0. What does it mean? So, mode shape, okay? For the mode shape, first mass, so here you have two mass, this is x1. If this guy this guy move 1 inch or 1 centimeter, then this guy will move how many centimeters? V2 gonna be 1.366. Or I can write this guy as a 2.0, 2.7, if multiply 2, 732? I'm sorry, what does it, well, 2.732, correct? So which means if I write the mode shape here, if this guy move 2.0, this guy will move 2.732. Its ratio is important, okay? Not the actual value. That's what the mode shape is. So it's relative motions, okay? So this is for the first mode, which is called in-phase mode. In-phase. Which is really, I give analogy for the marriage. So first week of marriage, first year, whole year of marriage, husband is always agree with the bride, always in mode, act together. Then maybe third year, as I said, husband doesn't agree. If he say, let's do this, and husband said, no, I don't want to do that. Well, and the lady said, let's do this. So it's out of phase. That's what the second mode is. Over here, second mode, when you plug in, so what do you expect here? It's very interesting because this is what the human relation agree completely with the mechanical system behavior. That's what that is. For the second mode, you do the same thing for R is equal to 2. So this is R is equal to 2. What does it mean? Second mode, right? Second mode. V1 is equal to, V2 is equal to what? Minus 0.366. Minus 0.366 V1. Again, ratio V2 over V1 is equal to 1 minus 0.366. So what does it mean in terms of the motion? The V1, this is x1, V1 goes to 1. Then V2 goes to minus 0.366. So Negative goes this way. How much? Minus 0.366 in opposite direction. This is out of phase. Out of phase motions. This 2 degrees of freedom model explains a lot. Or you can double it. If it's 2, then this is going to be twice of minus 0.366. Out of phase. Ratio is important, not the absolute value. I wrote that direction, but this direction is more realistic. First mode, same direction. Second mode, out of phase direction. So it's the same thing. Then total solution is concerned. So this is a mode, right? So mode, we have a solution already done here. We have a solution set here. For rth mode, you have a 2, then you have to have a summation, it's right here. And the CR and the theta R, you determine by initial condition. Okay, so we'll see that in a minute. Initial condition, you apply initial condition to get that. And the C1, C2, C1, theta 1, C2, theta 2, then you determine by the initial condition, as you will see in a minute. And we're going to go look at the property, modal property. They have a so-called orthogonal property of eigenvalues, which is in this case eigenvector. Orthogonal property of eigenvector. What does it mean? So when I say orthogonal property, it's really orthogonal of eigenvector, one eigenvector, with respect to the mass or stiffness matrix. Let's look at this, for example. We're going to consider R and S mode, two distinct modes. R is not equal to S, okay? Two distinct natural frequencies and mode shape. Then this is K phi rth mode, omega R square M phi R. So as you see here, this is for rth mode and this is for S mode. Two distinctive eigenvalue expressions here. So we're going to pre-multiply here, pre-multiply phi S transpose right here. And we're going to pre-multiply phi R transpose right there. Okay? So if you do that, then so this is the case, phi S transpose right here, phi S transpose. Second equation, phi R transpose, phi R transpose here, phi R transpose there. Then we're going to take the transpose of the second equation for the whole thing. If you take a transpose of this multiplication of matrix, what do you see? Then you have to change the position. If you take the transpose of the whole thing, then what you have here, if you take a transpose of the whole thing, then you will end up having phi S transpose multiplied by K transpose multiplied by phi R transpose of transpose which means back to phi r, right? Transpose twice. What does it mean, transpose? You just make a whole thing, say, make a phi, something like if you have a phi matrix, so you are dealing with the phi ij, then when you take a transpose of this guy, then you will end up having ji. You know that. Transpose, that's what the transpose means. So if you take a transpose of this guy, again, phi s transpose multiply by the K transpose, but K is a symmetric matrix. K and mass are the symmetric matrix. In structural dynamics problem, it has to be always a symmetric matrix. But when you apply the fluid to the structure system, then that generates the non-symmetric matrix, which has a fluid part and the structure part. That's a non-symmetric. But when you have a non-symmetric, by the matrix manipulation, you can have also symmetric expressions. Initial setup, non-symmetric. But for structural dynamics problem, no fluid, it's always symmetric. So it's a K is symmetric. If it's K is symmetric, what does it mean? Transpose is same as original matrix. Okay? So here take a transpose of second equation. So this guy transpose K transpose, then phi R transpose of transpose back to original. And the other side is omega s. So this side you have to also transpose the whole thing. This guy transpose, mass is the same, whether transpose or not, and this guy is right here, transpose of transpose. Okay, so that one is there. Then M transpose is equal to M, K transpose is equal to the K. Then you subtract the 2 from 1. Okay, you subtract this guy from that first equation, then the left hand side is what? Is identical, or left, this minus this, the left hand side is identical. You can cancel it, right? So what's the final dimension of the left part? This guy is, the phi s is 1 by n, right? Phi s is n by 1. Then take a transpose, which is then 1 by n, right? This guy after transpose is 1 by n. K is what? N by n. Then phi r is n by 1. The resultant dimension is what? 1 by 1, scalar value. Willis, you see that? So that's what, so it's a scalar value, quantity. So this minus this is 0. Okay? The scalar value is 0. And the right hand side is phi r, this is all same. This guy. So omega r square minus omega s square. This guy is just a carryover down here. That the left hand side is equal to 0. Then you will end up having that expression. So over here, omega r, omega s are not same. This is a distinctive, the natural frequency. So this is not 0. Then this guy has to be equal to 0 for distinct the natural frequencies and mode shapes. So this is equal to 0. This is what the orthogonal property of the eigenvector means. With respect to, in this case, is a mass, okay? With respect to the mass. If this guy is equal to 0, that's what the orthogonal property of eigenvector. If that is equal to 0, by looking back over here, over here, let's look at this guy here. S and R are distinctive mode and of course natural frequencies, and this is equal to 0 over here. So this is equal to 0. So which means right hand side is equal to 0. Then you have that expression, this is equal to 0. What does it mean here? I can say phi s transpose m times phi r is equal to 0, or phi s transpose k phi r equal to 0. This R or S business is really saying the distinctive S is not equal to R. That's what the implication is, okay? So this is, remember, this is orthogonal property of eigenvector or mode shape vector, so shown here. One more, orthogonal properties, that's what that is. Another one I want to introduce is orthonormal mode. It's kind of a little bit weird, but the two definition is very important when you run the commercial code for modal analysis. All the mode printed or generate by the code is orthonormal, so which is called orthonormal mode. What does it mean? It is the combination, so normal, orthogonal, then normal, orthogonal and normalized vector. That's what the orthogonal, orthonormal, so which is combination of orthogonal plus normalized vector. It has some nice features in there. Okay, that's what the two things. One thing is orthogonal mode. This is definition one. One is orthogonal vector, orthogonal property. What does it mean exactly? This is what the phi transpose m phi is equal to, this is two distinctive, if this is S mode, this is R, two distinct mode equal to 0. Or I can rewrite this guy as phi same m phi transpose is not equal to 0, or I can say some value, alpha value. If this is a 1, this is 1, then this is alpha 1. Non-zero. If it's the same mode, if this is not the same as this, then that's a 0. So orthonormal mode here is this. It's like if this is orthonormal mode, phi S transpose mass, this is a phi R, can you see there? This is equal to delta R SOSR. This delta, this is a chronicle delta. You heard about the chronicle delta? So this is equal to 0 if R is not equal to S. This is 1 if R is equal to S. Okay. So this is called orthonormal. So in this case, to distinguish the notation, I usually put N here, which means normalized, orthogonal vector. So just to put the N superscript on the left, saying that phi is normalized. So any commercial code, Nastran, ANSYS, Abacus, when they put it out the mode shape, they put it out the orthonormal mode shape. So this is very, very nice to simplify the result here. And the same thing I spelled out here. Same thing I spelled out here. Phi S transpose M, phi R, S and R are distinctive, that is equal to chronicle delta RS. Why this is, I keep saying this is nice feature, why I say that. So the reason is sometimes clear, but this is expression using the matrix forms. Omega square is a diagonal, okay, and as you see here, if this is the orthonormal eigenmatrix, then this is gonna be the identity matrix. Identity matrix, there is always 1 along the diagonal. Del RS, R is equal to S, is always is equal to 1. And we'll apply this to get orthonormal eigenvectors using 2 degrees of freedom system. So let's say this is not orthogonal, this is not orthonormal eigenvector, just eigenvector for the phi first mode, phi second mode. Okay? And small n in the superscript is normalized. Let, okay, is equal to alpha 1. That's what we have to determine. We have to find out. And alpha 2. Okay? Then if you pre-multiply phi transpose, then M, then phi, this is for the first mode, okay? Then you have a straight multiplication of this guy. This has to be equal to 1 because it's 1, 1. diagonal has to be 1 because chronicle delta Rs has to be 1 when R is equal to S. So you have this, right? Then this is equal to 1. So this guy is equal to 1, then you can determine the alpha 1. And alpha 2 you do the same way. Then you have that equation, you can determine the alpha 2, so alpha 1, alpha 2. Then you can find orthonormal, the eigenvectors or modal vector. This is the first mode. This is orthonormal eigenvector for the first mode and second mode. So now you have, if you put the 2, that's what you have. So this case this is for the first mode and this is for second mode. So back to the business here. Back to the business. Back to the business. If you back to the business, if you have a phi, I'm going to say n, which means normalized. First mode, right? Transpose m times n phi. This is, let's say, if this is a second mode, then what do you expect here? What do you expect? What's the value here? 0, right? Two distinctive mode, 1 and 2. But if this guy is 1, what do you expect here? What do you expect? 1. This is a 1. That's the beauty for when you normalize it. It's a 1. Then what happens if this guy is a 2? What happened? 1, same 1. That's the beauty. Sometimes very useful, as you will see here. That's the about the only difference. But in school environment, I really don't care whether you use orthogonal, the modal vector, or the orthonormal vector. It really doesn't make any difference at school. But if you're dealing with 10,000 degrees of freedom, you're dealing with 10,000 natural frequencies and modal shape, then it matters. That time, if you make a normalized the eigenvector, there are some conveniences there in the manipulations. So this is the way to get that, okay? So you can try this. You have this, then the first mode and second mode, you can have manipulation, whether you can have 1 or 0. Okay, next one is a response of discrete system by modal analysis. But usually for the DDAM, dynamic design analysis method, all you have to know is natural frequencies and the modal shapes. That's what you need. And mass matrix, which is really diagonal. So depend on whether I cover a whole thing in time or not. I will give you the DDAM problem. I'll decide Friday or Monday whether I should give you a DDAM problem or not, okay? Because it needs some calculation. It's not a heavy calculation, but you should understand 100% on what I'm doing here. Quantity you need for DDAM application from the modal analysis, natural frequencies, and mode shapes, corresponding mode shapes, and mass matrix is what you need. And to get all that, you can use any available commercial code, that's fine. And or MATLAB, if you can set it up the eigenvalue problem yourself, vice versa. Okay. And this is section F is response of discrete system by the modal analysis to get the response, applying the initial conditions. Okay. So initial conditions. So x is equal to phi eta, you saw many times, is a linear transformation. Rewrite here, this is in modal space. Got it? And take out the one ith row, is this. Then for the solution for this second order ordinary differential equation, you have free vibration equations, and which is equal to cosine plus sine. This is coming from the initial condition in modal space. So we have to find the expression, initial condition expression in modal space. So we know in physical space, x and x dot at t is equal to 0. That's what we know, but we have to convert that information in the modal space, which is eta and eta dot. Okay? So to do that, look at this carefully. X is equal to phi eta. No change is right here. Okay? X is equal to phi eta. I pre-multiply phi transpose m. Phi transpose m. Okay? And if you do that, phi transpose m phi, I said in general is mass bar. Okay? This is a diagonal, of course. If this phi is normalized, orthonormal, the eigenmatrix, then this matrix should be what matrix? Young one matrix. If this is orthogonal and normalized, called orthonormal eigenmatrix, then this is equal to Willis identity matrix, square matrix, if this is normalized. It simplifies quite a bit. Phi transpose m phi, this is identity matrix. Identity matrix times eta vector is eta vector itself. Eta vector itself is simply this. So what you need is eta at t is equal to 0. Another initial condition in modal space is eta dot at t is equal to 0 is all here. And x as initial condition, you know, x at t is equal to 0, x dot at t is equal to 0, you know. Then you can convert the initial condition in a physical space right into the modal space. Then you can solve the problem. That's what I'm showing over here. But you are not gonna really have a chance to do this to solve, except get the modal property, natural frequencies, and the modal shape, things like that. And the two references, all this information is taken from one chapter in Meyerowitz, Elements of Vibration Analysis. I happen to use this book to teach the vibration class in the PG school, but otherwise I just use this alternatively all the time. This is Thompson's book, Theory of Vibration with Application. This is very, very good book with lots of example problems, exercise problem. But this is, in addition, this is good book, but not many exercise problem. But some theory portions are very good. So this, the 18 page covers really everything on the modal analysis, okay? I think if you spend maybe an hour sometime this week, hour or less, I think you should have a very good understanding. Okay, so this and 7.3. Next two sections, 7.4, 7.5. This is really beginning of a DDEM approach, which is really changing the dynamic loading as equivalent static loading. Then ship designer can just use it. Not the ship designer, naval ship designer or naval submarine designer, they can really use it, okay? And this 7.4 and 7.5, I want you to understand the conceptual things, okay? Conceptual things, that's good enough. And one case is, this is like a response of one-dimensional multi-degree of freedom system to the shock motion. When you said the shock motion basis in excitation, right? Everything is mounted on the hull plate or on the deck or right on the plating. Some equipments you mount right on the wall, things like that. Then to the shock motion means, in this case, is a basis in motion. So this multi degrees of freedom, but this is all connected like in the one-dimensional matter. So it's called the one-dimensional multi-degree of freedom system to the shock motions, okay? So this is, let's say, n different the masses within the one cabinet. One shipboard equipment break down into n different components, okay? So this is, I can say, is mass here, all mass here, x1 all the way to xn. So how many degrees of freedom this particular model is? N degrees of freedom system. Okay, if n is 3, then there's a 3 degrees of freedom system. And basis in motion. Then what we have done for the shock spectra, if this is only one mass, then we define the relative displacement as x minus g, right? Same thing here, approach is identical. If this is x1, this is z, y is x1 minus g, okay? And if this is xn, then yn is equal to xn minus g, not that guy. Always relative to the base. Very important assumption to solve the problem, which make the system equation symmetric and orthonormal, make the life very easy. Otherwise, it's all coupled system, then you get lost forever. So, relative to this, relative displacement yn is what? Xn minus z. Xn minus 1 minus g is y n minus 1. x1, y1 is equal to xn minus z. Then when you really look at the result, it's a very nice orthogonal property it should have. So this is really simplest model. When you throw this guy into the modal space, of course, naturally, when you throw into the modal space, you can list out like a single degree of freedom model. So this is for eta 1, eta 2, all the way through the eta n. Okay? So it's a decoupled system. This is all connected, coupled system. So it's again beginning of the D-dam, and if you throw this equation of motion, my double dot plus ky is equal to minus mz double dot, identical format. Rather than a single value, you have a matrix notation. Identical, but definition for y is x minus g, the base excitation. Then you have all this beautiful material property: mass, diagonal, this K stiffness, symmetric matrix, and so-called positive definite, which guarantee the positive eigenvalue, which means a positive natural frequency. Otherwise, you will be a whole mess. Then now you have this, then you let y is equal to phi times eta. What I'm doing here? Modal transformation, right? So that's what I'm doing. Double dot is going to be this. Then you pre-multiply this guy into the here, then pre-multiply the phi transpose. Then you have this. Then over here, what's the m bar? Phi transpose m times phi, right? That's what the m bar. And k bar is what? Phi transpose k times phi. Then this is the diagonal matrix, k bar diagonal matrix. Whatever carry over here is just, you can spell out. This is so-called, as you will see, modal participation factor. Each mode does not contribute equally. So right-hand side is like a force to the system. And lower mode has a tendency to have a higher the force. So as it goes up, then modal contributions are slowed down. So here, if you use if you divide this equation by m bar, this is eta. K bar over m bar is omega n square, natural frequency matrix, who has only diagonal term. So then whatever the rest, it keep carrying over. Then you have equation, remaining equation. As you're doing that, you have that equation set. So this is in what space? Modal space it has. And you're just summing up everything as a p vector, which is called the modal participation vector. And if you pull out the ith row, which means ith mode, then eta I double dot plus omega ni square, eta I is equal to minus p I z double dot. It's ith mode. You pull out ith mode. Ith row, row means mode. This is in modal space. So here p, we put it everything shown here divided by m tilde or m bar. You have this. If phi is orthonormal matrix, this m bar is identity matrix. So inverse of identity matrix is identity matrix. So this is 1. So the result gonna be phi transpose normalized phi times m and 1. This is a modal participation factor. To use a DDAM approach to get the result, you have to compute the P. Modal participation factor you have to compute. Then to do that, it's nice to see that m bar is equal to the identity matrix. Then it's very nice already. So the one row you pull out over here, this is right here, cast into the fraction. So you have this phi. You may or you may not, as you wish, to normalize it, or simply orthogonal the mode shape vector or matrix you can use, or orthogonal normalized the vector or matrix, either way. So if you PJ spells out, you have the expanded form, this is matrix form, vice versa. It's a lot of material suddenly, but this is just a part of extension of the modal analysis. Have you seen this before? Yeah, this eta j, to get the solution for second order the ordinary differential equation in the convolution integral forms. You have this. Shall I continue, or you take a break for a few minutes? I'm gonna finish this up. So it's not much left. Shall I continue for another 20 some minutes? Are you tired? Sunu, it's okay? Just listen carefully, that's all you need. Chorong, you have a dinner, right? Jongwan, you have a dinner. I didn't yet. Well, the Willies have dinner, candy dinner. So let's keep pay attention. For some of you, this may be a little bit strange, but please look back my notes, and should be clear. Not clear, see me anytime. Then you can speak Korean or Bangladesh. What do you speak? I can understand. Then, well, Willis speak English. You speak Chinese? Oh, Mandarin?
Yeah.
Oh, not the Cantonese?
No, I speak Hokkien.
Oh, that's good. Okay, so this is really nothing but same from this equation, convolution integral solution. We have done that last week. And you see the integration of the z double dot. This is what the convolution integral in the spectral, shock spectral area. And then this is circled by red. is Vj, which is jth, the modal velocity, and the value in omega n is in the report. This is a Naval Research Lab report 1396. This is a declassified report since 1985. Before it used to be classified, but after some 30 years or 25 years, they declassified the report. That's the only reason you are able to see this report, to get all the design values necessary to apply to solve the shipboard equipment analysis. Okay, so this is in next section. This report, all the tables you need, I put that in the next sections. And the Vj is equal to this, is shown right here. Okay? And y is equal, if you know y, then you can determine the x. X is equal to y plus z. Okay? So it's very systematic if you look at my notes. But first time as you look at it, sometimes it's a little bit confusing, but as you calm down and read, it should really understand very easily. And this is the principle of superposition, and summation of all the modal contribution to the total response in every degree of freedom, shown here. And then to convert into the static value, no dynamic, you have to make independent from the time t. So then they use the maximum value. Let's say Hj is a maximum value of eta j. J is a mode. All over the t, you pick out the max. Okay? And every mode you have to do that. So designate as Hj, or Hj is equal to eta is Pj over omega j, maximum Vj for all over the t. Then I'm going to say that maximum small Vj in time domain, I'm going to call that as capital Vj, now which is an omega domain. So here Vj is a function of omega j. Okay, omega j. So then I can say maximum value. This is all time independent. Capital Y is a time independent, but omega dependent, because J is a mode. So Y vector J is phi j hj. Now it's a time is gone. Okay. So then Fj, this Fj is k times y is equal to mx double dot. You remember equation of motion for single degree of freedom system? Mx double dot is equal to ky. So this is what exactly that is. So this is now inertial force, but no time concept, because you are dealing with a max. So ky, so this is like you can call dynamic loading in static matter, static manner. So it's equal to k phi j h. So this is a mode. the forcing function modal vector. So if I just put the matrix form here, F matrix, the entry is a vector, first modal force vector, second modal force vector. No time concept, is maximum. Of course, which is not true, it's all approximation. I don't like it, but you have to design for equipment support. So what do? Then this methodology is still very valid, because when you apply, almost all the major amount of shipboard equipments has been used to this DDAM approach to design. So what can you say then? Then this is all jth mode, jth modal force, but total response goes like this. Some people use ABS, absolute sum. This method is not been used for long time. You can delete. This has a historical value. Absolute sum of the modal result, not used. And SRSS, square root of sum of square. This is very valid, but earthquake engineers are using this SRSS method. Shock people who design the naval ship use a little bit more conservative, modifying this SRSS is called the NRL sum. Naval Research Lab, NRL sum, to make it slightly more the conservative. How? From the SRSS, then you take out the higher modal response. Take out the higher modal response and take an absolute value. Then you have to remove, as you take outside of a square root, then you have to subtract that guy from inside. This is called the NRL sum. But this equation, strictly speaking, is wrong. But the more precise sense is this. This is almost the last page before 7.4a is this. Let Yij is relative displacement at the ith degrees of freedom, and the jth mode. If I do that, I have to do for every row, which is I here, this is a degree of freedom. Then every row, not the vector, every row. So you take out from here the maximum value, which could have a negative or positive, doesn't matter. Maximum, absolute max, take outside. Then you have to subtract that from the inside the square root. Okay, so here is maximum, the modal response. Let's say ith mode in this case. So this is a correct expression for this 7.4-6. Replace this to that expressions, okay? Then again, I'm doing the same thing over and over again until you feel I fed up, because to make sure you have a full understanding. The dynamic forces acting on the mass point. This is a dynamic forces acting on the mass point is minus m x double dot. Okay, mass times acceleration. X is y double dot plus z double dot. But we know eta j expression is like that. Then y double dot is a phi, eta double dot. Then phi is a matrix. Every column is, this is like a first modal vector or mode shape vector, second mode shape vector, all the way through, I said m, which is lower than n. I have a reason coming soon, eta. Then y double dot is this guy, eta double dot. And it's just the same thing. And rewrite this guy here. And I didn't give you any proof. Summation of mode, J is a mode. Phi J times Pj. Pj is modal participation factor. Always when you take a sum is equal to 1. Then rewrite this guy. And just to keep rewrite, then you have this expression. This is a time domain function because Vj, small vj, is a time domain function. If you take a sum of all the mode, should be equal to sum of all the physical force. Then Fij from here, ith is a degree of freedom, j is a mode. You have that expression. Okay, over here is still the function of t because Vj is a function of t. But when you take max all over the t, then it's free. It's no longer time domain function, but it's dependent to the mode omega j. So over here, omega j times Vj, I can say that's equal to Aj. A is acceleration. You remember in shock spectra, omega times velocity is acceleration, right? It's gone. It should be. So one of I took off my shoes. Sorry, it's more comfortable. When you have a forces here, you can construct as F1, F2. You will end up having this all the way through, let's say, Fn. This is a modal force, okay, modal force. So in this case, this is every mode. This is a first modal force. First modal force. If you do that, I can just write this as a forcing function. Forcing function as let's say, let's use this Fij. You need this value. The force matrix, I need a complete entry of this forcing function. I called Fij. This is what entry you need. And each entry is a force in every mode. Then you apply as a static force to the system. You follow me? Ultimate goal is we're gonna do the exercise problem, simple 2 degrees of freedom model. This is then you have a modal force. You have n different modal force for the time being. then this is a time independent because you pick out the max all over the T, then you apply this force. So here, this is ith rho means ith degrees of freedom, and here is a mode. All this is a mode. Then one pick out the first column means you put out the first column means first modal force, static force, apply that to the system. Then you got the stresses, deformations, whatever for the first mode, then second mode, third mode, fourth mode, and so on. Then you take the summation using NRL sum. Okay, so I'm going to apply that into very simplified problem set, then you would know better. So AJ come into picture, omega j, and multiplied by Vj is right here. But the question arises you know, for the people dealing with like a turbine pedestal design, okay, whether that's right or wrong for shock situation, then finite element model will provide maybe 100,000 node. You multiply 6, you will get roughly number of degrees of freedom, which is 600,000 degrees of freedom. How many mode do you expect? 600,000 the mode. Are you going to apply all 600,000 mode to do all the modal summation? That's ridiculous. You are not going to do that. Then what to do about it? How to do about it? Lower mode contribute a lot higher than higher mode. For 10,000, let's say 10,000 degrees of freedom model, you may need maybe 10% to include in the analysis, which means for 10,000, you take a 10%, maybe 1,000 degrees of freedom, 1,000 mode you may just need. Or maybe 100 mode, then maybe all you need. Then how to say that? How can you say how many mode should I pick out? Because as you look at the modal participation factor, lower modal participation factor is dominant. Maybe first to 10 mode, when you compute that may be sufficient to include. So how to do that? That's what the so-called 80% criteria is, what this page is talking to you. Then to do that, first you have to compute so-called modal mass. In the modal space, if when you compute the modal mass, okay, modal mass in modal space, take a total that has to be equal to the physical mass in the physical space. It doesn't matter what space. So total mass has to be same. Well, you can prove it very easily mathematically. To do that here, let's say summing all the forces in a mode, total dynamic force acting on the system can be expressed as like this. J is a mode, okay? I is degree of freedom. So for the jth mode, So jth modal force is equal to summation for all degree of freedom force. I is a degree of freedom, J is the mode. Then if you expand this guy, by the way, your node should be already I. This is, when I use I, that's a degree of freedom. J is a mode. So you have this expression, then reorganize it, then this has to be I. So this term, this is so-called the jth modal mass, okay, this term. All other term is a function of J, but summation is with respect to I, okay? Then if you want to compare this guy for the single degree of freedom system, Pj is only one mode, 1, this is 1, so this is m is only 1, so omega 1, omega natural frequency, then v 1 mode, so that's what you have for single degree of freedom system. So for this is called the jth modal mass. For the jth modal mass, you can express, for the expanded form is concerned, is like this, or we talk about that already. Then when you take a summation for the all modal mass, mj expression is right here. If you put that in, you have that expression. Then you can reset as a summation with respect to the degree of freedom, then which means all the summation of modal mass is equal to summation of physical mass. In common sense, it should be. Summation of all the modal mass has to be equal to summation of physical mass. But 80% criteria, this is there are two authors, Belsheim and George O'Hare, and Belsheim, they are still alive. I saw him about 2 to 3 years ago in the conference. And but they're still attending conference. He's mid-80s, I think. So 80% criteria. What that means here is you take the mode, you have to compute the modal mass, they keep adding from the lower mode. You know the total physical mass. You know that. Any code even show you what the total mass in your system is, because when you know the physical density of the materials and all that, you can compute total physical mass. Then you got that. Okay, this is 100,000 ton. Then you can compute the modal mass. You keep adding when j is equal to 1, j is equal to 2, j is equal to 3. Keep adding. Keep adding up to the 80% of physical. When it arrives to 80% of the physical mass, then you stop. Stop adding additional modal mass. So for for 10,000 the mode structure, when you add maybe 100, could be already 80% of the total mass. Then you stop. Then just use that mode which provide just over 80% of the total mass. You follow me? Follow me? Not clear? Really? If you understand, then it would be better. Oh, Hassan, 2 of you, tell me what I said, 80% the modal mass. 80% modal mass. After this section, we'll quit, okay? You know the total physical mass, right? Total. You know the total physical mass, right? When you're dealing with equipments, you know that total mass. Sooner, right? Yeah, that you know that. Then my question is, in the analysis, how many modes we have to generate the force, modal force, in every mode. Apply that modal mass as a static loading to the system. So the picking out number of modes is so important. For 100,000 degrees of freedom, 1 million degrees of freedom, you have 1 million mode. I don't want, you don't want to work on 100 mode, because we know by the modal participation factor, as the J goes higher, the modal participation factor is almost zero. That means you don't have to include zero loading, right? Modal participation factor multiplied by like a Z double dot is a force. When P is almost equal to 0.00000000001, you don't have to include that. So how to determine the lower number of mode to include analysis? You can compute. I have M total, I know. First, I can compute the modal. This is I'm going to write as a modal mass as like this. You can compute the first modal mass by the equation set here. This. Pj, you know, you have to compute the Pj. Pj, where is the Pj? Where is the Pj? Where is the Pj here? Pj is gone. It looks like a sleepy here someplace. Pj. You find someplace. Pj, right? Pj. Someplace there. So, Pj. You compute this Mj. Compute M. I have there already. So, M1 plus M2 plus M3. This is a mode. Third modal mass. Second modal mass. First modal mass. You compute that, right? You keep adding, compare with M total. When you add 3 modal mass, then compare with M total. When you add this, is it smaller than this? You have to add one more. Then compare this total with M total. Oh, then it's over. Then stop. That's enough. Use up to the 4 mode. Follow me? Should be clear. How to include the number of mode. Stop. Then believe it or not, lower mode has a tremendous contribution. Then sometimes 80 and 90% is there already. Then few additional mode, 80% criteria, done. Then what that means, in fact, even it has 100,000 degrees of freedom model, you might end up just using 10 mode. Okay, that's very nice. And that's what the 80% criteria is, okay? So that's what you have there. And independent support motion, this is just a conceptual. So I'll do this on 2 hours, right? So I'll do this on Friday. So 7.4a is a kind of a conceptual. If I do this, I don't have to come back on chapter 7. Let me see. Yeah, let's finish this. If I talk for a few more minutes, I can complete. Sometimes this is a conceptual, okay? This is a very good, this idea, very good idea, like submarine piping system. Submarines, surface ship, you know, it's very long, like length of the submarine football field length. Cruise, which is 3 times, let's say, Yongwon or Sangwon, you mentioned container ship is, length is like 3 times of the football field. You said
No,
that?
that's just the area.
Okay. Then submarine is like length is a football field. Yeah. Ballistic missile, which carries ballistic football field. Think about the piping running from the one end to the other. Football field once? No. Many times. Then when you have a football field, 400 or 500 feet long, and when explosion occurs, could be here, it's all different, and could be a independent excitation to the submarine and the submarine equipment. So how to handle that? You know, it's not like the one-dimensional multi-degrees of freedom system basis in one excitation. No. Look at this. Excitation here is different to this. So then this idea came up. This idea is done by George O'Hare, as shown here. Independent support motion. All the piping is, of course, supported by the tray, of course. If you go into the naval ship, you can see all the trays, snubbers, holding the piping systems and all that. Okay? So which is like this, holding. So this is a structure, like a piping systems or whatever. And KCB, C is like a structure, B is a foundations, KBB is holding the piping systems, you can say that. But to make it general, this is called XBI, XBJ, XBK, vice versa. And this is a kind of a support system. And this is for KCC stuff is piping system. MC, C is structure. Okay? Conceptual. This is all conceptual ideas. Okay? Then you can say that the equations of motions you can spell out this way. C, xc is displacement and acceleration vector of structure. C is a structure, B is a foundation, and MC is a structure mass matrix, MB is a foundation mass matrix, conceptual work. KCC is for structure, BB is for foundation, BC or CB is a coupling, connecting between the structure and the foundations. Okay, then you can cast into that forms. Then you can, this is a partition matrix, okay? Partition. This is a partition. So you can first open the first row. If I open the first row, MC times XC double dot, this is 0, plus KCC times XC plus KCB times XB equal to 0. Then you move the one term to the right hand side, you have that. So that last equation, then I'm going to, as we are familiar with YC is XC minus G type of the forms, I'm going to replace this expression into here. XC is YC plus G. If you do that, and you can have that equation. We are familiar with this expression. Then if I said this guy is equal to 0, then you have two sets of equation. One set is defining this expression defining Z, and this expression for solution of the response. So that two equation is in next. That equation is here, Z, and remaining equation is here. So idea is you can solve this equation. To solve such a long piping system problem, which is independent. It's going something here. This location don't know what's going here, because this is so long. This is independent motion ideas, conceptual ideas, okay?